Good morning once again. So this is our 750 economic growth. This is an elective for PhD students. And today we're going to discuss the solo model as our first starting point. But before that, I want to give you some insight about growth theory. So here we will either look at continuous time models or discrete time models. Okay. So Z here is the set of integers, R here is the set of real numbers, right? And most of the time, our models will have this state space form. You are now familiar with state space forms. There will be some variables, x's, where y's depend on these variables. And those x variables will evolve in time. Okay. So in the discrete time framework, you would basically write these in this way. Okay. Now here, obviously, x is called the state variable. And y's are called the control variables. Okay. So most of the time we express our solutions in this form, right? Because there will be a static equilibrium where if people take some decisions, if firms do certain things, they will find their optimal values, their control variables, as functions of their state variables, right? And then those state variables will evolve as well. Now, obviously, you can make these models stochastic by adding the error terms or fundamental shocks, let's say. Okay. So that could be the case if the models are stochastic, but most of the time we are not going to deal with the stochastic models. Okay, our interest lies in understanding F and G in the continuous time models and F and H in the discrete time models. Okay. Now in continuous time, if time is a continuous variable, the growth rate of a variable, let's say this is growth rate of x, okay, will be defined. Okay, so the growth rate of x will be defined in this way. Now x could be any variable. In the discrete time case, this growth rate will be defined in this way. Okay. So these are obviously percentage growth rates, right? These are percentage growth rates. We can also talk about gross growth rates, right? So if I talk about especially in the discrete time framework, we, for instance, can define g of xt as this proportional increase, and obviously this would be equal to g of xt, right? So there are some basic, of course, formulas, right? So if you in the continuous time, for instance, let's say you have this variable z, which is the ratio of x to y, okay? Then g of zt is equal to what? G of zt is equal to g of xt minus g of yt. If z is equal to xt times yt, then g of zt is equal to gxt plus gyt. So using this definition, you can actually prove such stuff. Okay. Here in discrete time, if you have zt equals xt divided by yt, what do you have? So the gross growth rate, g of zt, is equal to what? It is equal to xt plus 1 divided by yt plus 1 divided by xt yt, right? So you have what? Xt plus 1 divided by xt and yt plus 1 divided by yt. So at the end, you have 1 plus gxt divided by 1 plus gyt. Okay? So using the definitions, you can derive such growth rates both in continuous time and in discrete time. Now, what I want to do for the rest of this initial lecture is to talk about the famous solo growth model. All right, so this is Quartile Journal of Economics. And this is very simple model actually. Now, first I want to focus on a discrete, continuous time version. Okay. In this model, we have an economy, a closed economy. And in this economy, output is going to be produced by this very simple Cobb-Douglas technology. Okay. So here, alpha is between 0 and 1. Now, this output, of course, will be income, and income will be allocated to consumption and investment. So here we basically assume that savings are automatically transformed into investment spending, right? Then we're going to say there is a fixed saving rate, S. Okay? And finally, the change in the capital stock will be found in this way. Now, obviously, so here AT is productivity, right? And LT is labor. So these will be exogenous state variables, right? So here I will have A dot T equals G AT and L dot T equals NLT, where, okay, so here I have S between 0 and 1, delta is the depreciation rate between 0 and 1, G is the growth rate of productivity, which is exogenous, and N is the growth rate of labor force, which is also exogenous. Now let's look at the variables, right? So here, your state vector is what? It's K, A, and L, right? Because state vector will change as a result of your investment spending or consumption decision, okay? So control variables would be what? Y, C, and I, right? And parameters, of course, are here, alpha, S, delta, G, and N, right? So these three equations will tell you how the state evolves, okay? How the state evolves, but careful, it still depends on I, right? So we have to do some transformations before we write the state space form of the model, okay? So how do we do that? Well, very simple. If I have K dot equals I minus delta K and C equals 1 minus Sy, this implies I have I equals Sy, right? So K dot is Sy minus delta K, okay? And Y is equal to what? Don't forget this. It's equal to KAL 1 minus alpha, okay? Now in this model, A and L are always growing, right? So this means Y will always grow in this economy, okay? So there will be growth in aggregate terms. So to understand the model, we have to, to study this model, to find a steady state, we have to transform the variable, we have to detrend the variables, okay? So for this reason, we first define these variables. So this is capital per effective worker. This is labor output per effective worker, okay? This is consumption per effective worker, sorry. This is consumption per effective worker, and this is investment per effective worker. Now, once you do that, what you want to do is to understand the evolution of this variable, okay? And using this equation, so using this, and the laws of motion for these variables, you eventually get this, nonlinear differential equation, okay? So this equation is the fundamental differential equation of the Solon model, okay? And it has very interesting properties. So let me rewrite it again, rewrite here again. K alpha, of course, this is KT, right? And G delta KT, right? So there is a steady state. You can quite easily see it. So in the steady state, we have K dot T equals 0. So you have Sk alpha equals Ng delta K. Then you find K as, or you can call it K star, obviously, right? So it is like S divided by M plus G plus delta, 1 over 1 minus L, okay? You also see that, I'm sure you are familiar with this graph. So there is this linear part, right? Ng delta K. And there is also this Sk alpha part, okay? So when they intersect, we have our steady state, right? I mean, there's another steady state here, but it's a trivial steady state, right? K equals 0. We are not really interested in this one because this requires there's no initial capital stock. Oh, by the way, in such models, of course, we assume that.
Hocam, affedersiniz bölüyorum ama tahta biraz geriden geliyor hocam.
That's always the case. I'm sorry for this. I don't have any solution for that. That happened in the other semester. I mean, the previous semester as well.
Okay.
So that's it. You can also imagine understanding the sign of this, right? Since the derivative is negative at the steady state, this is the steady state. This steady state is, of course, stable. So you may want to show this derivative evaluated at the steady state is negative. Okay, so that's another exercise that you may work on. So you can also draw the growth rate, right? That's another interesting thing. So the growth rate of this variable is now what? It is SK alpha divided by K minus NG delta. So the growth rate of KT is this. Okay. So this is K. This is G of KT. So you have something like this. This is N plus G plus delta. Okay. Now, obviously, and of course, this is also the same equilibrium and it is stable. Now, what are we interested in? So this is output per effective worker, right? YT divided by AT and LT. And in the steady state, since this is equal to KT to the alpha, if KT goes to K star, YT goes to what? Y star, right? And this is constant. So these are constants, okay? But if YT goes to a constant, what is going on? If YT equals YT divided by AT-LT goes to a constant in the steady state, then YT-LT, this is GDP per worker, right? This always grows, and this is roughly equal to what? AT Y star, right? So the growth rate of GDP per worker must be equal to the growth rate of Y star and growth rate of AT. Growth rate of Y star is 0. Okay? Then if we denote it by, let's say, Y hat, okay, Y tilde T is equal to AT YT, right? So the growth rate of YT tilde will be equal to growth rate of AT plus growth rate of YT, but this will be going to 0 in the steady state, and this is equal to G at all times. So in the steady state, in the very long run, the growth rate that we are interested in is equal to what? Is equal to growth rate of productivity. Okay, this is one of the fundamental results of the Solo model.
Can we say the technology or productivity?
I didn't get your questions. Can we say what?
Technology.
Yes, I mean this is so. AT is an elusive term. So we call it productivity, but obviously when technological progress takes place, that productivity is larger, right? So this is technological progress in the most general terminology. But it appears in the production function, in the production function, it appears as a labor augmenting productivity term, right? So I have raw labor, let's say 5 workers, okay? But each worker has this average productivity AT, let's say AT is equal to 2, then if 5 workers work, they produce 10 units of labor services, okay?
Okay,
that's the idea. So this is the Solo model, and there is of course a discrete time version in your assignment. You're gonna work with the discrete time version and you're gonna simulate it in Excel, okay? But the model is very simple. It doesn't involve any dynamic optimization because saving rate is fixed, right? The society always saves a particular fraction of total income, and that particular fraction of income always transformed into is always transformed into investment. Okay, this point is the break-even point. This one here in that graph, the steady state is sort of a break-even point. So let's be careful with this. So this is the fundamental equation again. So you should be careful with that. So if you look at this, so this part is depreciation, right? This part is due to productivity growth because I am trying to understand capital stock per effective worker, right? So if A is growing faster, the depreciation is larger, okay? And here also I'm looking at effective labor, right? Capital per effective labor. So if labor force grows faster, I have to allocate more capital for each worker, okay, to sustain the same amount of capital stock per effective worker. All right, this one. So the implications of this model are what? The implications are this. So first of all, and this is the most important result, a capitalist economy where labor and capital are, they have, I mean, we have unit elasticity of substitution between labor and capital because Cobb-Douglas production function basically guarantees that. Okay, if firms in the economy can substitute worker with capital, unlike in the case of the Leontief model, right? Then this economy converges to a particular steady state. Along this steady state, GDP per worker will exhibit some growth if productivity growth is positive. Okay, so if I have G greater than 0, remember that G is the growth rate of productivity. If that's the case, then GDP per worker in the long run, okay, this is the long run growth rate of GDP per worker. Oops. It will be also equal to G. Okay. That's one important result. Another important result is that this equilibrium, this balanced growth path is stable, right? So you may want to imagine how variables change in time. Okay. Obviously, this economy is an economy of exponential growth, right? Because A is growing exponentially, right? Because if you solve this differential equation, you have what? AT equals H0 e to the GT. You have LT equals L0 e to the NT, right? And so on and so forth. So you have what? You have YT growing like this. You have LT, let's say, growing like this. So this is YT. You have AT, for instance, growing like this. So in okay, this is not correct actually. So Y should be faster. So maybe you have something like that. Okay. But on the other hand, you will have what? You will have, if you think of K dot KT, for instance, the growth path will be like this. So there is a steady state, right? And initially at t equals 0, let's say you have a level larger than this, then you're going to converge to the steady state. If you have lower, then you're going to converge to the steady state. The same is true for, of course, YT, right? You're going to converge to a particular level. Okay. Now the main problem, I'm gonna talk for about 2 minutes, then I will answer your questions. So the main problem with the Solov model, so Solov model is entirely innovative for 1956. Okay, but from the viewpoint of what we achieved after Solov, it's pretty simple and it has some problems. The biggest problem, of course, is that you cannot really understand G. Okay, so G is in Charles Jones' terminology, G is like a manna from heaven. Okay, so there's productivity and productivity always grows. Very nice. But the model does not tell us anything about how an economy can actually choose a growth path with a larger growth rate, for instance. All right, or the model does not tell us anything about what variables or what mechanisms will determine this long-run growth rate G. Okay, that's the biggest problem. Another problem, which is also very interesting and important, is that the model is designed to explain growth. Okay, the model is designed to explain growth, but in the very, very long run, we observe poor economies taking off to modern growth, right? So we observe, if you look at England, for instance, for long centuries of no growth, right? After the Industrial Revolution, the British economy started growing. So if you use the Solov model to explain long-run economic history, you cannot do that because this model predicts either always growth, right? If an economy starts with a capital stock less than the steady state, then this economy will always grow. It starts with a larger capital stock, then this economy will always decline in the studies per effective worker terms. All right. So we cannot really understand poverty and the transition to modern growth using this model. So these are the two biggest problems, and the later growth literature, as we're going to see over the course of the semester, as we're going to study these models, we're going to see that how the new models basically extend this framework to enlighten us about the growth patterns, the determinants of technological progress and the historical change. Okay, we have 4 minutes for me to answer your questions. Are you there, fellas?
Yes.
All right. So if you have any questions, you can now ask. This is the simple solo model. I'm sure you all studied the solo model, but in the assignment I'm going to post today, you're going to start working on a discrete time version, the same model, but the discrete time version, and you're going to execute. You're going to simulate this model in Excel. If you like, of course, you can use MATLAB or whatever thing you want to use. But in Excel, so this model is simple enough to be simulated in Excel. So that will be your first assignment. And next week, we're going to continue with the Ramsey model. Okay?
Okay.
All right. If you have no questions, let's call it a day, and I will see you next week. Okay?
Okay, thank you.
All right. All right, bye-bye.